first up, parabolas. When we're finding the inverse of a parabola, it's very important to keep in mind what constitutes a function, right? So I think it could have been back in grade 9 or even grade 8 already, probably maybe grade 10 actually, if I'm being honest. They'll chat about what is a function. So we know a function versus not a function. Right, so a function is when we either have one x value mapped up to one y value, or we have many x values mapped up to one y value. So for example, an example of number 1 would be a straight line function, right? We know that if I have one x value, oh, that's a y value, one x value, boom, boom, matches to one y value, right? One x value matches to one y value. This is a function then. An example of the bottom one would be a parabola. Right? We know parabola is a function. I mean, you learn about it when you do function in grade 10, so it must be a function. And we also know it's a function according to this definition, because I can have one y value and two separate x values mapped up to that one y value. Are you with me? Right, so that is still a function. So when is something not a function? It's any time that you have multiple y values mapped to one or many x values, right? So basically any time you have more than one y value for a coordinate. So I write that in x, y, it's when you have one x value mapped to many y values or many x values mapped to many y values. Basically, anytime there's more than one y value. Okay, examples of the above would be as follows, like a circle. If I plot a circle on a Cartesian plane, there we go, do I see that this one x value actually outputs two y values? So a circle is not a function. When we do analytical geometry, though, we treat it somewhat like a function because it still has x-intercepts and y-intercepts. But in terms of a definition of a function, a circle is not a function. And when we get into the inverse of parabolas, we'll see that we are dealing with not a function as well. Okay, so let's touch base on that. When I find the inverse of a function, okay, we need to remember, firstly, we're reflecting of the line y is equal to x. But everything that is x and y switches positions. So what was my x-intercept becomes my y-intercept and vice versa. What was my domain now becomes my range and vice versa. Okay, so you'll see that even coordinates, the coordinates will switch. So let's look at a normal parabola. I will make this parabola, let's say that this is f of x is equal to 2, let's just make it x squared, is equal to x squared. Okay, so if I need to inverse this function, I'm going to be reflecting over that line, right? Which means now that what was this point, let's say this point was -1 and positive 1, it can only be, and let's say this point over here was 2 and 4. Okay, when I inverse this function, the x and y positions of coordinates even switch. So what was -1 and 1 now will become 1 and -1. So we'll go to x, 1, -1, that point will now be over there, 1 and -1. Same thing over here, 4 and the 2 will switch. So now 4 and 2 will be over there somewhere. So we see that when I sketch this inverse now, it'll actually look something like that, reflecting over the line y equal to x. All my x and y positions switch. Alright, so if we look at the inverse that I just sketched now, we see that this in fact is not a function. because one x value, right, now outputs two separate y values. And we know from the definition that I did just before, that is not a function, right? I can't have many y values for one x value. So this leads to something very important about inverses of parabolas. We will always need to restrict the domain of your original function to ensure that your inverse is a function. Right, so what does that mean? I know I drew on the graph, sorry, but basically, if we look at where it becomes not a function, we see that it's after my graph turns, right? Because once my graph turns, then my 1x value starts to output two separate y values. So we are either going to need to only use one half of the graph. So that's where restricting the domain comes in. Okay, so what does this mean? Either we'll use this half or we'll use that half. So I'll draw that in a diagram. Just put some axes for me to work on. Right, so we know now, I'll use two separate colors, that when I have, because we are reflecting of the line y is equal to x, the line y equal to x, when I had this half of my graph and I reflected over that line, do we see that this is what the inverse will look like? Sorry, I should do it in black. Oof. Let's do it in black. That is what the inverse will look like, right? Because I'm reflecting it over that line. So either I would need to say, what is my x value turning point? How am I restricting my domain? X needs to be less than equal 0, which is the black part, right? To ensure that the inverse of that function is a function. Or, if I'm referring to this part of my graph, which then gives me that inverse, I would need to say x needs to be greater or equal to my turning point's x value to make sure that I actually have a proper function. Okay, so in essence, all you'll need to do is either say x less than equal your turning point's x, or x greater than equal your turning point's x, right? Both of those are fine because then it will give you a function. Do you understand? Because if we restrict my domain in this way, I will always be making sure that one x value outputs one y value. 1x, 1y, 1x, 1y, right? Or in this case, 1x, 1y, 1x, 1y, 1x, 1y. Okay. All right. Next video, we'll just chat about exponential inverses, which will be, because log graphs are quite important in grade 12 and it's tested quite often as well. But that'll be in the next video.